The next speaker is Keisuke Fujii, and he's going to talk about separations, even in the presence of noise. Thank you.
Okay. Can you hear me? Okay. My name is Keisuke Fujii from the University of Tokyo. And today, I want to talk about the special theorem for quantum supremacy, or we should say quantum ascendancy, following the talk given by Professor Chan on Tuesday. But anyway, here we're interested in the hardness of classical simulation of noisy quantum circuits. Especially, we are interested in the very noisy case where we cannot perform universal fault-tolerant quantum computation. But even in such a case, we can find a threshold value with which we can find a quantum advantage against classical computer. So this is the outline of this talk. I want to first talk about the motivation of studying noisy quantum circuits. And then I want to explain how to show hardness. And then I want to explain our main result, threshold theorem for quantum supremacy. And then apply this result to a concrete scheme, like a 3D topological cluster state computation, and also to the fault-tolerant computation with surface code. Okay, first motivation. So quantum supremacy is first stated by Professor John Preskill in the Solvay conference in 2011. And he asked that how can we best achieve quantum supremacy with the relatively small system that may be experimentally accessible very soon with 100 qubits. And actually, as you know, recently extensive efforts paid to realize experimental quantum devices for quantum information processing. And so now more and more accurate quantum operation are realized, and also more and more number of qubits are available. So now it's a good time to argue how to demonstrate the quantum advantage over the classical computer. And this is nicely also introduced by the previous talk by Sergio. And for this purpose, there are several intermediate models for quantum computation. Here, intermediate means that it's not universal, but still we can find some quantum advantage against classical computer. One example is boson sampling proposed by Alonso and Arifpov. And another is the IQP, which consists of the commuting circuit, like here, proposed by Bremner, Jozsa, and Shepard. And another example is the DQC1 model. This is a highly mixed state quantum computation with one clean qubit. And all these intermediate models are not universal, but physically, experimentally very motivated. This is because boson sampling is nothing but a linear optical quantum computation. And already we have several experimental demonstrations. And also, IQP can be implemented by using a Hamiltonian dynamics with Ising type interaction. And also, DQC1 is a model of quantum computation using NMR spin ensemble. So in this sense, these all models are physically very motivated. And the main purpose of this study, this work, is to add a new item to these intermediate models, namely universal circuit, but the circuit is very noisy. So specifically here, we're interested in very, very noisy region where we cannot perform a standard fault-tolerant universal quantum computation. So the motivation of considering noisy quantum circuit is here. So there is an ongoing project on which aims fault-tolerant universal quantum computation. Here is IBM and Delft QTech and John Martinez with Google. And all these projects, the target of all these projects is a threshold theorem. And threshold theorem states that if the noise strength is smaller than a certain threshold value, then you can perform universal quantum computation with an arbitrary accuracy, right? So here we have a threshold value, and below which we can perform universal quantum computation. And the threshold value highly depends on the model of fault-tolerant scheme, and also depends on the choice of the noise model. And specifically, if we choose topological fault-tolerant quantum computation on the 3D cluster state, or two-dimensional fault-tolerant computation with surface code, then further, if we choose a noise phenomenological noise model, then the threshold value is given something like 3%. And if, on the other hand, if we choose a circuit-based noise model, which is a more realistic noise model, where each elementary gate is followed by some depolarizing noise, in such a case, we have a threshold value which is something like 1%. And here we have a very natural question. So can we simulate the noisy quantum system above this threshold value? So this is very natural question, but the answer is somehow not so trivial. But at least we can say that in the phenomenological noise model, and the noise rate is higher than 14.6%, then we can fully simulate the system by using Gottesman-New theorem. This is because if a noise level is higher than this value, then the magic state becomes a convex mixture of power-based state. So in this sense, we can simulate in this region. But still, we here have a large gap between the quantum and the classical simulation simulatable regions. And one of the main motivations of this work is to characterize these intermediate regions. Okay. So let's move on to the how to show hardness in our proof. So we use a post-selected quantum computation. So the idea of post-selected computation is to solve decision problem by using conditional probability distribution. So suppose we have either quantum or classical probabilistic computer here. Here we have two kinds of output. Output X is used to solve the decision problem. And here another output Y. And this output is to use post-select some very rare events. And we solve the decision problem by using this conditional probability distribution condition on the Y equal 1. The important thing here is the probability of post-selection can be exponentially small, right? So you might think this is somehow cheating, because in actual experimental situation, we cannot perform this kind of post-selection. But still, this post-selection is useful to distinguish your system is quantum or classical. So, actually, if you apply a post-selection to the classical system, the system is result in the post-BPP. Class result in the post-BPP. On the other hand, if your system is quantum, then you apply post-selection, you result in the post-BQP. And Alison showed that post-BQP is equal to PP. PP is the probabilistic polynomial computation, which is one of the classical complexity class. And now here we have a classical computational class and another classical computation class. So we can directly compare these to class by using the polynomial hierarchy. So polynomial hierarchy is a natural extension of NP problem by using Oracle machine. And now postBQP, P with Oracle machine postBQP is included in the third level of the polynomial hierarchy. On the other hand, P with PP machine, Oracle machine, include whole of the polynomial hierarchy. So this indicates that if these two classes equivalent, then polynomial hierarchy collapses to the third level. So this indicates that if your system is potentially as powerful as postBQP under the post-selection, then your system cannot be simulated efficiently on the classical computer unless the polynomial hierarchy collapses to the third level. So this is very nice and useful way to show some quantum system is hard for classical computer to simulate. But there is a subtle point here. In this hardness proof, we require somehow strong notion of sampling, like a multiplicative error, sampling with multiplicative error, like this. So this is a sampled probability distribution, and this is ideal probability distribution. And here we have some constant larger than 1. So this is somehow a strong notion of sampling. And this is later improved to the sampling with constant additive error with L1 norm or total variation distance here. But still, this notion of sampling is very strong. So unfortunately, if there is a noise, small amount of noise in your quantum circuit, then these conditions are easily broken. So we cannot apply these conditions for a noisy quantum circuit. So we need a new framework. So let's move on to the main result. So main idea is here. So here we have an ideal quantum circuit which we want to simulate. So here we have two output and conditional probability distribution is used to solve PP complete problem. And our idea is simulate this ideal quantum circuit by using fault-tolerant version, which consists of the noisy circuits. And output is processed by using some classical algorithm. Then finally, we obtain the logical output X and Y, which simulates the ideal one. But here we should remember that we are basically interested in the very noisy case where we cannot perform fault-tolerant universal quantum computation. So we need another trick. So here we have another output Z, which has information about the error syndrome. And here we use a post-selection on Z on the error syndrome. So here we choose no error syndrome is activated. So by using this conditional probability condition on the null syndrome measurement, we simulate this ideal circuit. And our proof of spatial theorem consists of two parts. One part is to show exponentially small additive error between the ideal one and the simulated one is actually enough to show hardness of classical simulation of these output on X, Y, Z. And the second one is actually we can achieve this exponentially small additive error between the ideal one and the simulated one by using error correction under the post-selection. Okay, let's see the first part in detail. So first part is consists as follows. So we solve the PP complete problem. Specifically, we solve the majority set by using this circuit, ideal circuit, as done in the Alveson's work. And in doing so, we can calculate, we can lower bound the post-selection probability by the exponentially small value here. So by using this fact, we can show that if the distance between the ideal and the simulated one is exponentially close, then we can show that conditional probability is also very close. Actually, the distance, the difference between these two probability is smaller than 1/2. Actually, this is enough to solve the PP complete problem by using this probability distribution over x, y, z, right? And next part, so next part is how to reduce the distance, how to reduce the distance between the ideal and the simulated one, simulated one. And here we have a fault-tolerant quantum circuit which includes classical processing. And this circuit consists of the sequence of unitary gates. Here we have an ideal unitary gate UK, and which followed by a noisy one. Here we assume stochastic noise, which means that which can be divided into the ideal part, identity part, and CP map, right? And then the final output probability distribution over x, y, z is written in this form. And then this noisy density matrix is decomposed into the sparse one and the faulty one. Here, the sparse density matrix is defined such that under the condition of post-selection, so null syndrome measurement, the output probability distribution is proportional to the ideal probability distribution. By using this definition, we can bound the difference distance between the ideal and simulated output by using the operator norm of the faulty part, which is divided by the probability Q. Here, probability Q is a probability to get null syndrome measurement. So probability to post-select null syndrome measurement. And finally, this value can be evaluated by using the noise parameter epsilon. And if epsilon is smaller than some constant threshold value, then this value can be exponentially small. So finally, we conclude that there is a constant threshold value below which the output from the noisy quantum circuit cannot be simulated by using classical computer unless the polynomial hierarchy collapses to the third level. So let's apply this result to the concrete models like 3D topological cluster computation and two-dimensional fault-tolerant computation with surface code. So first, topological measurement-based quantum computation on the 3D cluster state. So here we employ measurement-based computation on a graph state of degree log n. And this corresponds to the commuting circuits of depth n. And also, we apply a very simple noise model. So noise is independent single qubit dephasing with probability E. And then the faulty operator is decomposed into the two parts. One part is the faulty part corresponds to the Clifford operations. Another is the faulty part corresponds to the magic state distillation. And these two operators, the operator norm of these two operators can be evaluated. For example, Clifford case, we can evaluate the operator norm by counting self-avoiding walk and given like this. And then we can calculate the threshold value for the Clifford part like here, so 0.167. And then we can also calculate the threshold value for the magic state distribution, and it's actually given by the 0.146, because in this direction, magic state distribution is tight. So now you realize that the threshold for the Clifford operation is much higher than the threshold for the magic state distribution. The threshold for the quantum supremacy in this model is determined purely by the magic state distribution. So let's return to the slide for the motivation. So now we find that if the error probability is smaller than this threshold for the magic state distribution, the classical simulation of the system is hard. So in this sense, we find that all regions in between universal and classical simulation can be characterized as hard for classical computer to simulate, right? Then finally, I want to apply this result for a circuit-based noise model, which will be more interested in the experimentalists. And here we consider the two-dimensional lattice and use surface code and two-dimensional nearest neighbor gates on the square grid lattice. And the noise model is circuit-based depolarizing noise model. So each preparation and measurement and single qubit and two qubit gates are followed by some depolarizing noise with probability P. And in this case, the thing is slightly complicated because we have a correlated error. So in this case, we have to take into account the correlated error on the lattice. But still, we can model this system as a phenomenological model by cleverly defining effective single qubit error rate. So here we have an independent error rate nu and correlated error rate mu. And by defining this value as an effective single qubit error, we can model the system as phenomenological model. And by using this, we can calculate the threshold value in this case, and the resultant threshold value is something like 2.84%. And again, in this case, even in this case, this is determined by the distributivity of magic state. And important thing here is this threshold is much higher than the threshold for standard universal fault-tolerant quantum computation, which is 0.75% obtained in the same noise model. So this clearly shows that the noisy quantum circuit, which is achieved in near future or already achieved, is enough to show quantum supremacy, so quantum advantage against classical computer. So let's summarize this talk. Sorry. Oops. Okay, let's summarize this talk. So we show that noisy sampling from the noisy quantum circuit can exhibit quantum supremacy if the noise rate is smaller than some threshold value. And this threshold value for the quantum supremacy is much higher than the standard threshold value for the universal fault-tolerant quantum computation. And the interesting point here is that the threshold value for quantum supremacy is purely determined by the distributivity of magic state. And it is somehow natural because the magic state is necessary for universality of quantum computation. And so now it's very interesting to ask how can we verify or directly identify such quantum supremacy in noisy quantum devices in near future. So thank you for attention.
Thank you very much. We have time for 6 or 7 questions. In the back.
Hi. Yes, I think I may have missed. So many of the previous quantum supremacy complexity theory results rest on some conjectures, to establish that this bounded error simulation would collapse the polynomial hierarchy. Is there a complexity theoretic conjecture, or is there a conjecture that, your result assumes?
Sorry, could you say more loudly?
Oh, I was just wondering if this result rests on a conjecture, like, for example, the conjectures that...
Yes. Yes, actually, this result is based on the conjecture that polynomial hierarchy does not collapse to the third level.
But there's no further conjectures, like, for example, in the Aronson paper, there's this permanent of Gaussian,
In this case, we do not need another conjecture.
Thank you.
More questions? I have a question. So you showed the threshold result for universal computation. I wonder what happens if you restrict the model. Say if you say you only have logarithmic depth circuits or you have DQC1 circuits. Is it still true? Can you still have a separation and a threshold result?
I think it's a very good question, and in the IQP case, with constant depths, I think we can derive the similar threshold for quantum supremacy. But in the case of DQC1, I think it's very difficult to derive some threshold for quantum supremacy.
Okay. Can you elaborate why? What's the difficulties?
What's the difficulty? In the case of DQC1, yes, there is less measurement fault. So we cannot use the toric for the post-selecting some null syndrome measurement.
Okay.
So that's the reason why it's difficult to derive the similar things for DQC1 model.
Okay, understand. More questions? If not, let's thank our speaker again.